Okay, good morning everyone. So today we will briefly review the basic related to the semiconductor device. So how the typical device operation and how they are being fabricated. So it's basically the overview, the major contents what you will be learned from semiconductor physics device and related processing. But because this class is not mainly focused on the device physics and processing, so we will only use probably like 1 week, just to briefly overview the basic related to the semiconductor device. So first of all, just a brief overview that what actually is what the semiconductor is compared to the other materials here. So from all of the materials, we can divide by the 3 different types of the material. The first one is insulator. So the insulator means that this is a kind of material that shows a very high resistivity. So this is an axis related to the resistivity. And that also means that this is a material that has a very lower conductivity. So basically, that's what we expect for the characteristic that insulator could have. So we have the insulator that should have the high resistivity, also the very low conductivity. On the other hand, we have the complete different material that opposite for the insulator, which is inductor. A conductor, sorry, that's a conductor. So compared to the insulator, that for sure the conductor is a material that has a very low resistivity, but also that means a very high conductivity. And one of the conductor we will very often use in the semiconductor device, which is aluminum. So basically we will use aluminum or even the copper as a interconnection line, or some like a metal a skin. So basically we will use a copper or aluminum. And the semiconductor has a material property that's just exactly in between the insulator and also the conductor. So that's why we call this as a semiconductor, because the semiconductor has a characteristic just half like the conductor. So you can see from the name, we have the semi here. So that means that we expect the semiconductor should have the characteristic similar to the conductor, but of course the conductivity is lower and the resistivity is higher compared to the conductor. And one of the most important semiconductor materials for sure this one. This is silicon. It's the most important one here. So although when we talk about semiconductor, we always focus on the semiconductor, but to be honest, actually we will use all these 3 kinds of material. So in the semiconductor device, not only we use a semiconductor, we also use the insulator. We also need to use a conductor. So let's just use a MOSFET as one example. So in the case of MOSFET, we have the source, drain, and then we have the some metal here. And we also have the dielectric in this region. And on top of dielectric, we have the gate. So this is our source, this is our gate, this is our drain. So first of all, in most of the case, we simplify our case, so we will use a P-type silicon as one example. So this is a P-type silicon. So that is a material for semiconductor. So if you look at the typical structure for the MOSFET, so we actually will all use these three different kind of material to fabricate our device. So first of all, we have a semiconductor. So in this case, which will be the substrate. So substrate is based on the semiconductor materials. And in addition to semiconductor, we also need to have the conductor. So that would be the gate, source, and drain metal. So basically, we will still need to have the conductor in this region. And especially, we prefer to use some very special metal that can give us a very lower resistivity, because we want to have very high conductivity. We want to reduce the resistance in the metal. And also, we also will use the insulator, which in this case is a dielectric. So this is our dielectric. So we also need to have the insulators in this region, because this insulator has a particular function that can allow us to form the electrons in the channel. And also this insulator can help us to reduce the leakage current, which we will talk about later. So overall, although the class focus on the semiconductor device, but in reality, we actually need all these three different materials that can help us to form a semiconductor device. And regarding for the insulator, the most important insulator, which is silicon dioxide. Silicon dioxide is one of the most often used dielectric insulator that we can use for the dielectric in the MOSFET structure here. So that's first, just to have a brief overview for the different kind of electronic materials that we can use for our semiconductor device. And next one, we still need to brief overview again that what will be the available semiconductor material that we can use, for example, use for our channel, use for our substrate. And for sure that we have to look at the periodical table. So in the periodical table, we often use a semiconductor material coming from the group 3, group 5. This is group 4, group 3, and group 5. So these are the most important species in the periodical table that we can use for the semiconductor applications. And then in terms of the group 4 here, the most important one for sure is silicon. So silicon often is the group 4 materials here. And with group 4 material in here, for example, the silicon and germanium. So basically, we can already make the semiconductor device based on these elemental material. So that's we call as an elemental semiconductor. So that means we only need one kind of the material that's enough for us to make the transistor, the semiconductor device here. On the other hand, we also need for the compound semiconductor. So the compound semiconductor is a combination of the two different kind of species here. In most of the case, it's a combination between the group 3 or group 4, so that we can form the compound semiconductor. For example, here, aluminum phosphide, aluminum arsenide. So this is a combination between this one and this one, or the combination between this one and this one. Or for example, the gallium phosphide, the combination between this one and this one. And also one of the compound semiconductors that already in our daily life electronics, which is a gallium arsenide. So that's a gallium arsenide. So gallium arsenide that has been already commercialized. So in lots of in your cell phone, you actually already use a gallium arsenide high frequency electronics. And also there's other some of the material, for example, the indium phosphide. That's also very promising for the high frequency application. And beyond this, this is a 2-element compound semiconductor. Actually, we can also make the compound semiconductor that has 3 different elements. For example, we can form the compound semiconductor called as indium gallium arsenide. So that can be possible to be formed as a stable material that we can use for the electronic device. Or aluminum gallium nitride. That's another very famous example that we have already used aluminum gallium nitride based electronics for the lots of application. And also not only the compound semiconductor means the combination of the group 3 and group 5, we actually also can consider the group 4 as a compound semiconductor. So if we can actually make the device that can based on the combination of the silicon and carbon, so that's we call the silicon carbide. Or we can have the material that has a combination between the silicon and germanium, so that's we call as a silicon germanium here. So basically we can use all kind of the species in a group 3, 4, 5, and then make all kinds of different semiconductor, either as an elemental semiconductor or the compound semiconductor. So one of the very special property for the semiconductor material is that although it's called a semiconductor, but actually the semiconductor has a huge range of their resistivity. So you can see the category here that the semiconductor shows a very wide range of resistivity. That's from the 10 to minus 8 up to probably 10 to 4. Even beyond, we can make the semiconductor that shows an extremely high conductivity. And the reason that we can make the semiconductor that we can change their conductivity is mainly because we can have the dopants inside. So the purpose to have a dopant in the end is become, in terms of a device, in the end it's become we can have the N plus in the source drain region, and sometimes we can have a P minus in the substrate region here. So that's why this plus or minus, that means this material has a different concentration, and therefore we need to find a way to control the concentration of this device or this material. So that's why we need to have the dopants here. And in terms of dopant, there's two kinds of dopants. One is usually we call as a donor. And another one is usually called as an acceptor. So the donor is one introduce electrons and create the N-type silicon. First of all, we need to understand why the donor can introduce electron. So basically, the donor is in the list of the group 5 category. So group 5 category, that means we have the 5 electrons in the outer shell. So imagine this is the lattice arrangement. So we have the silicon, atoms as an arrangement here. And as you already know that in case of a silicon, the reason we call this as a group 4 because in the outer shell, the silicon contains 4 electrons in the outer shell. That's why we call this as a group 4. So therefore, we understand the electron, the silicon has 4 electrons in the outer shell. So if we put the silicon side by side, then actually we can make sure that each silicon has each silicon atom can form the covalent bonds with a nearby silicon due to this one electron is contributed by this silicon, and this another electron is contributed by this silicon. So therefore, we can make sure that the silicon and silicon atoms can form the covalence bonds in between. So that means each silicon atoms contribute 1 electron to form the bonding with the nearby atoms. But if right now we have the one group 5 material, for example, the arsenic here. So arsenic has 5 electrons in the outer shell. So that means we have 1, 2, 3, 4. But now we have 1 additional electron. And that's why this electron becomes the free electrons. And these free electrons can create the N-type silicon, because in this region we dope the arsenic. Actually, we can have the higher electron density. The high electron density, that means this is material that would towards the higher concentration, more like the N-type of material. So this is a reason why we call this as a donor. And then the donor's name is actually coming from the donate. So I think everyone should be very familiar with the meaning of the donate. That means you give somebody additional, you give somebody something. So the donor is also means that this is a type of the species that donate additional electrons. That's why we call this as a donor. And on the other hand, we have another type of the material that we call the acceptor. So acceptor is also, this is a word meaning coming from the accept. So accept, it means that you actually accept one thing from somebody else. So that's what we call the acceptor. And acceptor is introduce whole and create the p-type of silicon. And in this case, the only possible that we can have a possibility to accept something that could coming from the group 3. This is because, again, we assume there's a silicon atoms here. So we all know every silicon can contribute 4, and that means we can use a 1 to form the bonding with the nearby atoms here. But now if we pick up the group 3, for example, the boron in this case, so that means we only have 3 electrons in the outer shell. So we only have here, here, and here. So the boron can only form the bonding with nearby 3 silicon atoms. And in this case, this boron will introduce empty space. And this empty space can allow some additional electrons. This empty space can accept 1 additional electron. So that's why we call this as an acceptor, because once we introduce a boron in our silicon material, the boron, because the boron only has 3 electrons in the outer shell, so the boron will create 1 empty space, and this 1 empty space will allow the boron being able to accept the electrons from somebody, and these electrons accepting, that also means the Hall generation, because in the electronics world, actually the Hall is a meaning of the coming from the missing of 1 electron. So basically the Hall just opposite compared to electron. So once we have the empty space to accept electrons, that means this material can introduce another Hall here. So that's why we can start to make this material to work more like the p-type, because we have a higher Hall concentration here. So that's why finally we found out that the amazing part for the semiconductor material is that we are able to dope the different kind of species. We are able to manipulate their doping concentration. In the end, we can manipulate their conductivity and resistivity here. So usually the plus here, it means heavy doping. So that means this is a place where we have the very high doping. And then the minus here, that means we have the light doping. Sometimes for the more like the general talk, we call the high doping, but if you look at for the textbook or the literature, they actually call this as a heavy doping. But they actually it's the same meaning, but just a different wording. So that's the first things you need to know related to how we can form the different concentration in silicon by dope with a donor type material or the acceptor type species. So donor type basically can introduce electron, then acceptor type can introduce a holes. And in terms of a crystal structure, so the silicon crystal is cubic. So that means that each silicon atom has 4 nearby neighbors. And this is just some schematic of the silicon, and this has been already shown in the last slide. And also, when we all know right now the silicon actually is forming the covalent bonds with this is our covalent bond, forming the covalent bonds with the nearby atoms. But once the covalent electron break So that means we start to have the conduction electron. We have the conduction electron. Just assuming here, this electron can start to move because of the breaking of the bonds. But since this electron is moving away, so that's also the empty space is created. So empty space is created, that means also the hole is also created. So that's I think so far it's a pretty like a basic related to some of the electron hole generation due to the breaking of the bonding. But now we need to move a little bit further. That why do we need the quantum physics? So quantum physics or quantum mechanics is always the first and then the most difficult part. When you start to read the semiconductor books related to physics, and we always introduce the quantum mechanics in the first chapter. I think it's mainly like the second chapter, because the first chapter is always describes the latest arrangement, and second chapter we start to describe the quantum physics. In reality, the quantum physics is pretty complicated that you can definitely buy one book is completely talking about the quantum mechanics. If you are following the physics department course, in the physics department probably spend one semester in talking about the quantum physics. But luckily, we are the engineers, so we actually don't really need to fully understand everything related to quantum physics. So we can just understand the key points that can relate it to the semiconductor. So in here, we will just use a few slides to explain why we need a quantum physics. So the basic idea is that because we need to describe the electron movement in the micro world. So that's the purpose, because when we try to understand the electron is so small carriers, and try to move on in the so small scale place. So we found out that there's some difference compared to the typical physics. The typical physics we refer here is mainly means Newton mechanics. So if we have a large object, so that means we have a large things, and usually the Newton mechanics works very well. But in the case with a very small world, especially down to the micro or even the nanometer world, actually we found out that the Newton mechanics cannot explain lots of things. So the problem we try to understand is you have the piece of the semiconductor material here. Now we try to understand if there is electrons try to move from the left to the right in the semiconductor material, what actually this electron, the situation of that this electron will face, and how we can understand this electron's behavior. So if we try to room in this activity, that the electron move from here to here, actually the real problem for this case is that we consider the electron moving in the periodic structure. Because as you already can foresee, in terms of a semiconductor material, that means the semiconductor material is basically composed by the lots of different atoms that have the periodic a lattice arrangement, just like this one. So this is one typical semiconductor material that we have been already shown in the previous slide, for example, silicon case. But now we try to understand if there's a free electrons want to move in this region, what actually the issue of this electron will face. So actually this electron, what if you look at in the eyes of this electron will see a lot of the interactions, especially the potential interaction with each atom. So once electron move here, the interaction between this one and this one for sure is higher because it's pretty close by. And then once it move on here, the interaction between the nearby atom is getting smaller because it's far away from the atom. Again, the electron moving in here, the interaction between this one and this one is also higher. So of course, we are the engineer, so we actually pretty focus on the potential point of view. So actually, this reflect that the real issue for electron moving in this periodic structure is actually the electron moving in the space with a periodic potential, because the potential is suggests the interaction with the nearby atom. So if you getting pretty close with the other atom, for sure the potential between electron and nearby atom is higher. And then if the electron moving in the space without any atom, for sure the potential is lower. So now the real problem we try to understand is there's one electron trying to move it in the place where has a periodic potential. So in this case, the electron can be first moving in this direction, or unfortunately, we might also have electron stocking inside this potential well. If the electron is being located in this potential well, what will be this electron's behavior? So this is the issues that actually we are trying to understand. So in summary, again, initial problem is electron movement in the one semiconductor material. But if you look at closely inside this semiconductor material, the semiconductor material is composed by the regular periodic lattice arrangement. So that means the question is moving becomes electrons moving inside this periodic potential and a periodic structure. And because of this periodic structure, that also in the end, the electron is movement inside in the space where has a periodic potential. And there's two possible cases. The first one is electrons moves in free space. And second one is electron moves inside this potential well. So now probably you start to have some sense that if you already follow the semiconductor lecture, or you already follow the quantum physics, you start to feel something like the term you have heard, especially related to the potential well. This is term that we often refer to the case when we talk about the quantum physics here. And now, because in this class we are not spend one class to talk about the quantum physics, so I just directly jump to the conclusion. So the conclusion is that if you look at the conventional, the typical Newton mechanics, so if we talk about the Newton mechanics here, and then actually we only if there's one so if there's one carrier flow try to move to the right against one some of like walls here, based on the Newton mechanics, there's only one possibility can be happen, which is the refraction. So that's how the Newtons teach us that if you have one kind of the objective, try to throw against the wall, and there will be only one possibility happen is the refraction of these things. But this is not enough for the semiconductor, because of this will cause a lot of the trouble that we cannot explain what we actually observe in our semiconductor electronics. So now the quantum mechanics, the conclusion for quantum mechanics is trying to telling us once you have the electrons moving toward the wall, the same. Of course, first we have the reflection, and then the second, not only reflection, we can start to find out that there's a possibility of an electron can tunnel through the walls here. Just imagine that right now you throw the balls against the wall here. If you are actually in the quantum physics wall, so once you throw the ball against the wall, you will actually find the balls can penetrate the wall and reach to another side. So this is actually how the quantum mechanics telling us. And what's actually this imply for us? This is actually implies that even we have this kind of a potential, periodical potential, just as described before. But now, if we have the electrons inside this periodic potential, actually it is possible this electron is able to move to another wall. Even this electron is located inside this potential wall place here. And this is usually in here, we call this as a barrier. And this phenomenon is generally called as a tunneling. And now, the electron in this place cannot be determined precisely, can be only determined by the probability. So that's, in the end, this is the main conclusion we learn from the quantum physics, that when the electron is moving inside the semiconductor material, first of all, even there's some barrier, there's some potential wall, the electron might still be able to tunneling. But after the tunneling, we cannot determine the electrons precisely. We can only use the probability to describe how high the chance of electron can move in this place. So that's how the quantum physics teach us. Okay, so far, probably still get very confused as to why we still have to understand the electrons movement inside this periodic potential. So now we will also talk more about the application of this the quantum mechanics here. The first one, we need to still briefly overview that the main basics and main foundation behind this quantum mechanics is based on the Schrödinger's wave equation. So this wave equation is proposed very early time that we call as wave mechanics here. And there's a three assumption here. First one is by the principle of quantum and also the wave particle duality, and then also the conservation of energy. In the end, we can use a phi st is a wave function. So this is a wave function to describe our carrier here. And if we put the wave function inside this Schrödinger's wave equation, in the end we can have the conclusion as shown me here. This equation talk about this is a wave equation. Originally is depends on the x is a space, t is a time. In the end, this only depends on the space. So this equation tells us the wave function is a probability density function and is independent of the time. But what does this mean for us? This means that actually the position of the particle is related to what we are interested in. For example, electron and holes can be only founded in terms of probability. So that means the main difference between the classical and quantum mechanics is that the classical mechanics, we can determine the particle or body precisely, but in the quantum mechanics, we can only determine the particle. As a term, we use a probability. We can only find the probability of this particle, but we cannot determine this the carrier of the body very precisely. So that's how the quantum mechanics tell us. But in the end, by using this knowledge, finally we are able to understand one of the important characteristics inside the semiconductor device. So again, we can use a MOSFET as an example. So this is a source drain, and we all know we have the dielectric here, and on top of dielectric we have the gate metal here. So right now I think everyone is pretty familiar that the operation of a MOSFET is we give the gate bias. At the meantime, we give the drain bias. Once our gate bias is larger enough, we start to form the inverted electrons below. And because we also apply the positive drain bias, so this electron will be able to attract it and flow to the right and become our drain current. So this is the IDVG curve. So that's why we have the threshold voltage here. But the one thing we don't mention before is if you try to measure the leach current, gate current from the gate side, actually you will still be able to sense the gate leach current. But this completely contradicts to what we understand for the insulator, what we expect the function for insulator, right? So as you know, insulator should be the material that cannot have any carrier or electron conduction here. But how could possible you have the gate voltage here, but you have the electron here? Why the electrons can be moving across this dielectric and reach to the gate side, become leak current, right? If you just use a typical classical physics, that doesn't make sense, because this is insulator. Insulator just like the wall. So you have the lots of the balls trying to throw against this wall. It is impossible to have the balls happen here, because classical physics doesn't teach us here. So if you try to measure the gate leak current, IG, VG, you actually will find out that the current is increased as a gate bias increase. So this phenomenon start to struggling us, because this phenomenon cannot be explained by the classical physics. But luckily, we have the quantum physics. So quantum physics tell us you have the carrier here, you have the potential well here, but the quantum physics tell us this carrier, it is possible to be tunneled to the another side and then become the leach current. So now we can still redraw this kind of the schematic as shown in here. If we have the dielectric like this way, and then we have the electrons in the left hand side, which is actually the electron in the bottom. But now we apply the positive gate bias here. So based on the quantum mechanics tell us this electron is able to tunneling to the other side. So this phenomenon is we call as a tunneling. So that's why these tunneling electrons is become the gate leach current. And then this schematic, which is very similar to the case we talk about here, because this potential barrier, actually the dielectric insulator, that also will form as this barrier. And now we are trying to understand the electron movement when the electrons face as a one barrier. So now we can finally understand why even less insulator, we still possibly to have a gate current here, and that's also reflect to our measurement result. So these all can be possibly explained by the quantum mechanics here. So that's the purpose why the every first few chapter of the semiconductor is all talk about quantum mechanics, because in the later we mainly try to understand the semiconductor device behavior based on the the foundation of the quantum mechanics here. So that's a overview for our quantum mechanics. I hope that this can give you a certain more practical sense, not just related to this equation. This equation sometimes is a little bit confusing, yeah, because of if you only look at this equation, probably you cannot have the real sense that what this real impact on a semiconductor device. But if we talk about the gate-lead current, that's one of the very classical example that we need to understand the gate-lead current based on these quantum mechanics. Okay, so the next one is that with regarding for the free electron movement, so we have been shown in terms of the two-dimensional periodic lattice arrangement, if one's electron moving from one place to another place, this kind of the phenomenon can be also understood by considering the band model. The band model is the model that we have the concept of a conduction band, valence band, and also we have the in between the conduction band and valence band is a band gap. And this electron move from this place to the other place can be also schematically shown here from the moving from this place across this band gap and moving to the conduction band. And in general, this is how we call as a band diagram. So the electrons in the conduction band are the conductions or these are the mobile electrons. So once these electrons moving in this place, and finally this electron is able to be conductive, so they can free to move to the any place. And since we introduced a concept of band gap, so we need to look at what actually the band gap in the different kind of the materials here. So in silicon, we have the band gap around 1.1 electron volt. And in germanium, we have a very small band gap, that's around 0.6 electron volt. So based on the previous, these kind of the knowledge, we understand that once the carrier is moving from the bottom to top, that will become the current. So once we have the small band gap material, that means electron is easily to across this band gap and reach to the conduction band. So that's become the current here. But that means as long as this becomes smaller, the electron is actually easier to across this barrier and reach to another side. So that means this material easily to have the electron flow, which reflect to the leakage current inside this material. On the other hand, if we have another extreme material, for example, like the diamond, and the diamond has a very wide band gap, as you can see from here to here. So that's extremely large band gap. So electrons here is likely have no chance to moving from the valence band to the conduction band. So that means the diamond have a low leakage current. This is pretty makes sense for our daily experience because we all understand diamond, it should be a material very similar to the insulator, right? So we already know that diamond is one of the hardest material on the world, but also diamond should not very conductive, should have very high resistivity, and should have no current flow in the diamond. So this phenomenon can be also understood by using the band diagram. So finally, the band gap, the larger or smaller band gap can reflect the property of the electrons transport inside the material. Of course, diamond is an extreme case, but in between the diamond and silicon, we also have the other material has a slightly lower band gap, but it is already relatively large than silicon. For example, the silicon carbide or gallium nitride. Generally, they have the 3 times larger band gap than silicon. So this kind of material is often referred to the material that has a wide band gap material. And one of the promising characteristic for the wide band gap material is because the wide band gap material has a lower leakage current. Has a lower leakage current. And why we can draw this conclusion that wide band gap material ideally has a low leakage current? Because their band gap is larger. So the larger band gap, that means the electrons here is very difficult to move from here and jump to the conduction band. So that's why one of the promising characteristics for wide band gap is we have a low leakage current. And low leakage current also sometimes suggests this material is good for the certain high temperature application. Because the leakage current is very low, so even we try to put this in a very high temperature environment, the leakage current is still very low. So that's why the wide band gap material is generally very promising for the high temperature application. So now, I believe with the introduce of the band gap, this kind of concept, we start to correlate our daily experience for the one material. For example, this is very consistent with what we expect for the diamond. If you look at for a certain dielectric, for example, silicon dioxide, silicon dioxide has a band gap more than 9 electron volt. But silicon dioxide is a material that is perfect for insulator. So everything now makes sense because of this band gap. It also certainly can reflect the property for our electronic materials. So that's why the band diagram and band gap is very important for us. It's a very important tool for us to analyze the semiconductor device phenomenon. And also, this band gap or this band diagram can also as one of a way to understand the donor and acceptor, this kind of the knowledge. So assume we have the band diagram like here. So we have the EC and EV here. So previously we already know that the most amazing part for the semiconductor material is that we are able to dope our material. In the end, we can adjust the doping concentration. So for example, if we try to have the donors inside the one species, this donor can also be understood by considering the donor level inside the band gap. So once we put the donors inside our material, actually the donor will form the donor level as shown here. And of course, our goal is trying to make sure that this donor can contribute electron as larger as possible, can contribute as many electrons as possible. That means this gap should be smaller as possible, right? Because if this gap is smaller, that means we actually have lots of electrons is easily being jumped from the donor level to the conduction band. That's in the end becomes the conductive electron here. So ideally, we should have the donor that can give us a very small difference between the EC minus ED. And this EC minus ED is what we call the donor ionization energy. So usually, in the case of silicon, this ionization energy is very small. It's only 50 milli-electron volt. So this EC minus ED is called the donor ionization energy. So basically in the silicon world, most of us can almost ignore this donor level, because this donor level, this ionization energy is very small. So that means every in the electron in here can easily jump to the conduction band and contribute to the electron. So in the silicon world, basically we all consider this donor level, this ionization is very small. But this concept is pretty important when we talk about other material. For example, especially when you talk about the wide bandgap material. In the case of wide bandgap material, this donor energy, this donor ionization energy sometimes is relatively large, and thus becomes a certain problem for our wide bandgap material. So in here we won't talk about the what actually the concern in terms of in the case of wide bandgap. Just to let you know that everything can be quantified by consider the band diagram, by consider the energy level inside the band diagram. And on the other hand, for sure we have the acceptor. So still the same. In the case of acceptor, we have the band diagram EC minus ED. Then acceptor, it means that the acceptor is going to contribute to the host. So usually we draw the acceptor like here. This is a acceptor energy level, and this is EA. So similarly, EA, this is EV. Similarly, EA minus EV is acceptor ionization energy. So that's how we define this as a acceptor energy level and also the acceptor ionization energy. But in general, these ionization energy are pretty small, so usually we don't have to worry about this in the case of silicon. And also, by using the band diagram, we can also use the band diagram to understand the difference between the insulator, conductor. So semiconductor is something we have been shown. For example, in the case of silicon, we have a 1.1 electron volt. But in the case of a silicon dioxide, we have a huge band gap. That's up to 9 electron volt. So that's why we can expect the electrons flow inside the insulator is very difficult because of this huge band gap. And then the conductor has an overlap of this band diagram. So that's why the electron can easily flow inside the conductor. And next one is that we need to also discuss a little bit about how we start to accurately to calculate the carrier concentration. Because the problem is now we know we cannot precisely determine our carrier. We cannot precisely determine the electrons and holes. But now we hope have the one way to precisely calculate the concentration. So therefore we need to start to come up with something related to what we call the density of the states. So basically, energy band diagram is a collection of the discrete energy state. So the concept that why we call the energy state is because of in previous assumption we already say that we have the concept called the energy quantum. Let's show me here. The principle of the quantum here is introduced by the Planck. And if you have already followed the course related to the modern physics, probably you start have a little bit sense about this meaning of the quantum. So in here we don't explain in detail. In general, it's just that the band diagram is a collection of the discrete energy state here, and therefore we can count the number of states in the very small range of the energy delta E in the conduction band, and therefore we can start to have these density states here. So this probably, if you ignore this one, first you don't look at this one, just look at this one, EC and EV. So this is exactly what we already mentioned for the band diagram, right? So this is conduction band, this is valence band, and this is inside this is a forbidden band, and then this difference is what we call the band gap. But now we all know if we want to have the electrons movement inside this material, electron need to be across this band gap and reach to the other side, reach to the conduction band. So first things we need to know is how many states inside this conduction band that can have electrons. So that's why we have to calculate the density state in this here and in this here, because once electron is moving here, so electron will try to occupy some state in this region. So first we need to understand how many states here. So that's why we'll come up with a concept of the density state here. So these are the equation for density state. This is for conduction band. E minus EC, and this is for the valence band, EV minus E. This is for the valence band. This calculation, in the end, the equation is very simple. So I just want to say that sometimes the mathematics and physics in the beginning it looks complicated, but in the end, the goal is trying to simplify the phenomenon and derive the one equation that people can easily understand. But in the process of this equation calculation, sometimes it's challenging, but in the end, the conclusion is always very simple. Just like the case of the quantum mechanics. If you try to understand the wave equation, try to understand every detail in the equation calculation, that's very complicated. You need a lot of the patience. You need a very good skill set of your mathematical calculation. But in the end, the phenomenon, the physics conclusion, in the end, is very simple. Just like in the case here. So just don't be afraid to for this equation, because in the end we actually don't need these complicated equations, but that's just in the process. And another is important is we need to start to figure out the electrons. As we already say, we can only determine the electron in the way of a probability. So now we have to describe the probability of finding the one electron at a one energy state here. So that's we have to apply the equation, what we call the Fermi functions here. So now I hope that everything for you can be get more connected, because in the beginning we talk about the electron movement in the micro world. We say we cannot use Newton, we have to use quantum mechanics, because in the end the Schrödinger's wave equation proves that we can only determine the carrier in terms of probability. So that's why in here we start to introduce a probability function to describe that finding the one electron at a certain energy here. And then of course there's a lot of probability function, but the one we will use very often in the semiconductor is what we call the Fermi function. Sometimes we call the Fermi-Dirac distribution function, or sometimes we call the Fermi-Dirac statistic. So the equations look like in here. So that's how these equations look like. And the EF here is called the Fermi energy or Fermi level. So that's very important, because if you start have the chance to work on the semiconductor device, if you start need to use a band diagram concept, you definitely need to understand whether the Fermi energy is inside your band diagram, because Fermi energy indicate the characteristic related to the electron or holes here. And we can apply the Boltzmann approximation. So therefore, this equation can be simplified as shown here. E minus EF over KT, exponential minus E minus EF over KT is equal to here. So if we try to plot the Fermi function inside our energy, band diagram. So that would be look like in this case. Of course, right now you still get very confusing. I think it's pretty normal that if you don't have a background or you don't study semiconductor physics before, so far it's still very confused that why we have to have the density state, and then next why we still have to plot the probability. But the most important is the next slide, because next slide explains everything. In the end, if we try to calculate the electron concentration, just remember our goal is try to calculate the concentration for electron and then the holes here. So we just plot the electron concentration is the integration of the density state times our Fermi energy. And if we can use the graph to understand this calculation, this is our density state where we already described before. This is our Fermi energy here. So that means this integrated with this one or this one, and then in the end this area is become our electron concentration, which is equal to this Gc times the Fermi energy. And on the other hand, the same, this one also gives us a whole concentration. But the powerful for the Fermi energy is not only in the case. In this case, it's pretty Fermi energy just in the right middle between the conduction band and also the valence band. The most important case is that if the EF is not in the middle, if the EF is close to the conduction band, if this is our EF, and what will be the conclusion here? So if this is our EF, still this is our Fermi Dirac probability distribution function. So once we EF move upper, so that means our distribution function will also move upper, right? So now we have a new distribution function. And with this new distribution function, integration with Gc, so now you can see the overlap region is increased. The overlap region increase suggests in the end we have the large area as shown me here. So that's a N0 plumb here. Also, if right now we have our EF is close to our valence band with the same application of the Fermi energy, we can expect our Fermi Dirac distribution function is become in here. And now the overlap region for the hole is increased. So finally, you can completely forget the concept of the density state of Fermi energy, of the Fermi probability distribution function, but you still need to understand the EF here. So the conclusion here is that if our EF is close to our conduction band, that means our electron concentration is increased. That means this is an N-type semiconductor material. On the other hand, if our EF is close to EV, and then that means our whole concentration is increased. So that means this is a P-type semiconductor. So in the end, if we don't understand the density state, we cannot remember the meaning of the density state. We cannot remember the Fermi-Dirac probability distribution function. But you need to at least understand if the meaning of the EF here. So once our EF is close to our conduction band, that means we have a higher electron concentration. If we have the EF close to the valence band, that means we will have the higher hole concentration. That would be more like the P-type. So in the future, we actually won't draw the band diagram with such complicated drawing. We actually will only draw the band diagram with EC, EV, and if this is an N-type semiconductor material, so that means our EF will be close to our conduction band. So in the future, once you read the textbook or literature, everyone will only draw the band diagram with a simple EC and EV, but the EF will either close to the valence band or close to the conduction band or close to the valence band, and that suggests that this is a material more like the N-type or P-type semiconductor material. So that's the purpose why we need to apply the density state or Fermi-Dirac distribution function. Of course, in the next slide, we'll talk about some of the equation that you can use a hand calculation, but the hand calculation is mainly used for the homework or for the exam. For your research, most of us now, we can simply use some software to help us to calculate the concentration. We can use the software to determine this band diagram, but at least you need to go through the process once and how actually the fundamentals behind this calculation, how we come up with this conclusion that the EF can determine your carrier concentrations here. Okay, so we will take a break for 10 minutes. We'll come back in the 10 minutes afterwards.还没吗？还没，叫什么名字？林冠汉。boss 是一个。等我一下，没事。
电风扇怎么关？就是你知道遥控线啊。
你看后面找一下。
哦好。
对对对，等我一下。哦，林冠汉是不是？OK OK 好。OK 好。谢谢。
我是想跟你说，我就是有时去找学生，
对对
了解。
对。好，你先。
我想问上课对，老师你刚刚讲到 IGBT 的时候，我有点没有听的仔细，然后
简单来讲说，就是说你本身你的 gate curve， 你的这次有 gate insulation， 你有 dielectric， 那 dielectric 理论上它是一个完全的绝缘，那绝缘的话理论上是不会漏电的，所以你这边加 B 去电它是不会漏电的。
对。
但是为什么你的电子可以有办法穿过这个来去到另外一边变多电流？
我觉得有需要的一个机会。
对，这就要有量子力学来解释。
所以这个图是在什么样的状况下会画成这样？
就是给 bias。这个 IC 元件。
所以那不是假设以一个正常模式的元件，那不是应该是可能到了
理论上
程度，然后才突然有？
没有不会，它其实只要有加速，它就会慢慢反复上。
哦，就是慢慢一直有它到。
对。所
以说，就以那个 SiO2 那样子，就是它可能那个对，
也还是会有。
哦，所以就是很大，但
还是会有，一定会有，对，它一定会有这个，一定会有另一个，对，它只是它的电流的大小，因为 sense 10的负10，10的负11，其实就是有多少电流传过去，所以那其实就是一种几率的概念，
数量级的，
对，那就是一种几率的概念。
然后我还有，就是刚刚最后我不确定我笔记这边抄是不是对，但就是这个它多一个1是
没有，其实就是把这个1减到这上面是1减 EF， 上面是 EF 减 E。
那它不是只多一个负，还是
你可能算一下。对，我觉得确实这样。对，要多了1减对。
好。然后还有做一件事情，就是我记得老师之前说，就期末有分数。对。那个是我们自己。我是会分。你也分。我会分。
大概在期中之后，期中都可以分。然后要那个 retention。
好，是什么？
我们到外面跑，因为它是会录音。对，你会被录进去。 Okay, so based on the concept we previously discussed with considering the density states and also the probability function. So in the end, we can have this analytical equation where our electron concentration is equal to NC exponential minus EC minus EF over KT. And NC is shown here, which is a constant. And NC is called the effective density of states for the conduction band. And also we can have the whole concentration is equal to NV exponential minus EF minus EV over KT. And then NV is effective density of states. For the valence band. And based on this equation, we can also understand N becomes higher when EF moves to EC. So this is consistent what we have already shown here. Once our EF is close to EC, N becomes higher. So that also can be seen from this analytical equation as shown here. And also P becomes higher when EF moves to EV. And also, this is another plotting to show that this is EC, EV, and this is EF. So as you can see, when EF moves close to EC, and actually the concentration is higher. So this is a case for the ND and NA. So when EF moves toward the EV, and NA is become higher. So there are some additional concepts we will introduce here is the N times P and also the intrinsic concentration. So in an intrinsic semiconductor, so when we call the intrinsic semiconductor, that's we consider the case electron concentration is equal to hole concentration is equal to Ni. That's an intrinsic concentration. And Ni is intrinsic carrier concentration, and in the case of a silicon, Ni silicon is equal to 10 to 10. So that's a rough number we will use very often. So this is around like 10 to 10 here. And we also know about this equation previously. So if we have N times P, that will be equal to NC NV exponential minus EC minus EV over KT, right? Because of this EF can be cancelled. So we only have EC and EV left here. And also because N is equal to P, so N times P is equal to Ni squared here, still equal to NC NV exponential. But now because of EC minus EV, which is also equal to band gap. So that's equal to Eg over Kt here. So now we can further derive this equation as Ni is equal to NCNV exponential minus Eg over 2Kt. So now we can start to try to correlate our band gap versus our intrinsic carrier concentration. So if we have a material has a larger band gap, just show me here. That means our Ni is decreased, right? And also from the previous analysis from the band diagram, we already expect if our Eg becomes larger, that means our leakage current is smaller. So now we can still also get the same similar information, and also the temperature also will influence our Ni. So that means with this correlation, where your band gap increase, your Ni decrease, your band gap increase, our leakage current decrease. So we start to know Ni and leakage current might have a certain positive correlation. So that means Ni increase or I leak is increased. At the meantime, the temperature factor is here. So that means the temperature increase, the Ni is increased because this is exponential minus. Let me rewrite this again. So the temperature increase can lead to the Ni increase, but Ni increase also leads to the leakage current increase. So now these all very consistent to what we have already discussed before for the band diagram. So the purpose to have the band diagram is that we can almost forget this equation, but with the help of the band diagram, we can already certainly to understand the correlation for each the impact come from each factor. For example, temperature, the band gap, the intrinsic carrier concentration on the characteristic that we are interested in. For example, the gate leakage current in this case. Okay, so this is just another short summary. So now I think everyone here can immediately tell what kind of material this is. This is a semiconductor, but the EF is very close to EC. So this is N-type. And the EF is close to EV, so that's a P-type. And this one, we have a huge, large band gap, so that's an insulator. And also, we will have the overlap between the conduction band and valence band, so that's a conductor. So finally, we finish the basic you should know related to the one piece of the semiconductor material. But as already said, the most amazing part for semiconductor material is we can put the different dopants, and then we can have the P-type or M-type semiconductor. And therefore, we will definitely be interested in to understand if we try to combine with the two different materials. So what will be the physics and characteristic change if now we consider the material 1 and material 2. So that's a general like we will be interested in the semiconductor. And then the next is this still limiting the one semiconductor material to the another semiconductor material. But how about if we are trying to put one metal on top of semiconductor material? So that will be the metal and semiconductor. So this is already the case we previously have been mentioned, that's limited by the two different kind of the characteristic. One is a Schottky, another one is ohmic. So basically, if we try to put a metal on top semiconductor, we will form one of these two type characteristic. And then the last one for the structure we are interested in is first one, we have a semiconductor, and for sure we have the metal. This is metal. But how about right now we inserting one insulator, for example, silicon dioxide. So that is actually MOS type, right? So these are the all. So basically, when we talk about the semiconductor device, we have to do our best to understand the four kinds of the different scenario. The first one is we already mentioned, one piece of a material. So that's the first one. So we already have this basic understanding of how the carriers movement in the one material. And the next, we will upgrade the challenge. Now we are interested in if we put the two different material connected with each other, and how actually electrons will be able to move inside these two different material. Especially, we are particularly interested in this junction. And third one is this one. As already said, we have the three kinds of material: semiconductor, insulator, and conductor. So basically, when we try to understand semiconductor, we just try to mix every possibility combination. So this is the third one, is a combination of the conductor with semiconductor. So therefore, we will be also interested in this structure, and also the junction characteristic in between. And the last one is we just put all of the materials we know, metal, conductor, insulator, and semiconductor, and put all of them together to understand how the carriers movement, how the carrier transport in this type of the device. So this is MOS type. So now you can see why, if you are following the semiconductor physics class, you can probably, first chapter is always talk about a piece of material. For example, silicon material, how the lattice arrangement, and so on and so on. And second chapter is always talk about the quantum mechanics. But third one, we start to get more complicated, but we will start to talk about the two different materials put together. But usually the third chapter is talking about the junction, especially, for example, the PN junction, because we are particularly expect if we put the two materials side by side, connected together, the most difficult part we want to understand is definitely in the interface in between. So if you look at the semiconductor books, they always has one specific chapter related to PN junction. After PN junction, they start to talk about the PN diode, because PN diode is a one completely device. But the key influence that can determine this PN diode characteristic is this junction in between. So understanding the junction is always the key. Understanding this junction is always the key for us to understand the whole device behavior. So later on, when you talk about the metal semiconductor, it's always the first thing we have to understand is the junction between. And when we talk about the MOSFET, when we talk about MOS type, we will spend the major effort to understand what happened in here, because this is the most crucial region that will completely determine the whole device characteristic. Okay, so now for the material 1 and material 2 combined, we can use the PN diode as the most basic structure. So PN diode is basically you try to put the P-type doping combined with the N-type doping, and then in between we will form the metallic junction, which usually we call as a PN junction. So first things we have to understand is that if we only consider the diffusion, so you may know that I think that's come from the high school physics. If there's a high concentration of one species in the one area, by considering diffusion, for sure, this is a P region, so you have a higher hole concentration. So the diffusion tells us that the high concentration, the particle or species that has a high concentration will prefer to diffuse to the region where has a low concentration. So that's because of due to the concentration gradient. So that's why we have the diffusion as a one possible transport. And on the other hand, this is an N region. So N region means that this is a place where we have a high electron concentration. So we can also expect the high electron concentration will try to move towards the left because of due to the concentration gradient. But if we only have a diffusions happen in between, that means all of the holes will diffuse to the right and all of the electron will diffuse to the left. And after a certain moment, the hole concentration here will be equal to hole concentration here. The electron concentration here will be equal to the electron concentration here. So that means after certain time, this piece of material where have the P and N in left and right in the end should become N equal to P in the left. and N equal to P in the right, because the diffusion try to make everything back to the balance. So they try to have the same concentration no matter in the left and right. In the end, we all become the N is equal to P in the whole piece of this material. But for sure, based on the knowledge you expect, this will not going to be happen. So that means there's another mechanism try to stop this diffusion mechanism. So that's the things very interesting in, because we are naturally come out with another mechanism that will let the diffusion dominate the whole process. So that's the keys to understand the PN diodes here. So again, when we consider the PN junction or PN diode, first, this is a schematically to show we have the P on the left, we have the N on the right, and once we have the P here, we have the concentration Na that represents the whole concentration. We have a concentration of the Nd that represents the electron concentration. So as we already know, because of the concentration gradients or concentration difference between these and these, so we can expect the whole will try to diffuse to the right. On the other hand, the electrons will try to diffuse to the left. So this still will happen. But if we try to look closely, because of the electrons diffuse from the right to the left, that means we will start to have the positive charge donor atom will left behind, because this is ideally the region where have the negative charge and the positive charge. But once you have electron move to the left, that means this positive charge donor will start to appear at this place. So similarly, if we have the holes flow from the right to the left, we can start to expect there's a negative charge of acceptor appears. So that means we will have here. So now, because due to this diffusion, we start to see in the right hand side there's a positive charge. In the left hand side there's a negative charge. And usually this is a region we call as a space charge region. Sometimes we also call this depletion region. Depletion region. The space charge region is sometimes, if you try to understand from the Mandarin translation, sometimes also get very complicated, also very confused, because in the lots of the Mandarin-based textbook, they just translate as a 空间电荷. So to be honest, the 空间电荷 didn't help us to understand a lot by the word's meaning. So my suggestion, just remember there's a term specifically called the space charge. It's happening because of you have some charge left, and then you have some charge remaining. So that's why we call as a space charge. Although sometimes we also call the depletion region. So lots of the terms in the semiconductor, if you try to on purpose to translate in the Chinese or in the Mandarin, sometimes also doesn't help us a lot because it's a pretty unique professional term. Just remember that as a term, that's all. You don't have to really understand the meaning come from the words. The most important is to understand the physics behind. So now, because we have the space charge region here, we have the positive charge, we have the negative charge, and by naturally, this positive and negative charge will start to form the electric field in this direction. So we will start to have the E field in this direction. And also, because we have the Hall diffusions toward the right, so that's a Hall diffusion. We have the electron diffusion toward the left. So now we can finally to understand why the diffusion will not continue happen because of this electric field. This electric field will try to push the Hall back to the left because of this E field. We'll try to, you have a Hall diffusion here, but this electric field will try to push the Hall back to the left. And also this electric field will try to push the electrons back to the right. So that's the sense why in the end we won't have the piece of material that's completely has the same concentration everywhere, because of these charges in the right and left, because of this space charge in the end to induce an electrical field, and this E field will stop the Hall diffusion, will stop the electron diffusions. This phenomenon can be also understood perfectly by using the Venn diagram, because as we know, the Venn diagram is a very useful tool. We'll try our best to use the Venn diagram in everywhere. So by using the Venn diagram, we don't have to draw the schematic, the very complicated schematic like I drew before. So with considering Venn diagram, the left-hand side is a p-type material. So that means if we have the EC, this is a conduction band, this is a valence band. Because the left-hand side is a p-type material, so that suggests our Fermi energy, EF, should be close to the valence band, right? So that's finally, if you forget all the equation, it's fine. But these things you still need to remember. Once a p-type, that means EF is close to EV. And on the right-hand side, this is n-type. So n-type, that means this is a conduction band, this is a valence band. The n-type means our EF is close to the conduction band. And this is a case under the zero bias. So zero bias means our Fermi energy is constant everywhere, because this is a zero bias. But now you still probably have already observed to be aligned with the left-hand side band diagram, with the right-hand side band diagram. And also, we are all talking about the silicon. In this case, this is silicon, this is silicon, this is silicon. So band gap still will be the same. The conduction band, valence band will be the same in all the systems. So that means the band diagram in this region will be look like in this way. So this is the depletion region or space charge region where we have been talking about. By consider the band diagram in this case, we can further try to use the band diagram to understand why the electron cannot move to the left. So as I already mentioned, diffusion means the electron will want to move to the left. The holes, diffusion means the holes will want to move to the right. But from the band diagram also tell us this is the conduction band. So that means we have the electrons here. But now the electrons move to the left, we'll see the huge barrier. We see the huge barrier here. It's just like they need to cross this mountain, but it's very difficult because of this mountain is very high. So that means the chance for electron to across this mountain, to across this barrier, is difficult. So that's why we won't see the electrons move to the left anymore. Also, we have holes here. So the holes cannot move to the right because this barrier, this mountain as well. So finally, we can completely forget what we have been talking about in the last slide. By using the band diagram, that can already help us to visualize so many physics, so many electron or hole transport. And the band diagram can already help us to understand the device physics here. So the mountain here is actually as a potential barrier. But in here, we have the spatial name for this potential barrier. It's how we call the VBI. The VBI is the built-in potential. The reason we call it built-in is we don't do anything. We don't give any bias. We just put this material connected with each other, and the potential is already generated. It's already there, so that's why we call this as a built-in potential. Of course, we are not satisfied to understand the case at a zero bias. We definitely will be interested to know what happens if we apply the additional either forward or reverse bias. So now if we try to look at the case of the forward bias. So forward bias means that we apply the positive voltage in the P region, which is we call the anode region. In the diode, we have the anode, we have the cathode region. So we apply the bias in the anode region. And once we apply the bias in the anode region, we can start to see the barrier here is reduced. The barrier reduced is because right now we have the gap in this Fermi energy. So now you can see the Fermi energy is not connected in the left and right because there's a voltage difference. And there's a voltage difference that will create this barriers difference. In the end, our our potential barrier, our built-in barrier here in between the left and right is reduced because now the barrier height is become the VBI minus VA. So once the barrier is reduced, the probability of electrons to move towards the left is higher. And similarly, the holes possibly can start to flow to the right here. So now we can start to expect, if we put the IV curve, whether we have a current versus a voltage. Once we apply enough bias, we start to have the current come out. And this is usually we call as a VF, that's a forward turn on voltage here. So that's why under the forward bias, our IV characteristic is shown like in this way. So under the forward bias, the smaller potential barrier, lower electric field. So the hole can diffuse to the N region and electron can diffuse the P region. And besides, there's a concept with a minority carrier. Minority carrier, it means that we have to understand what the difference between the majority and then the minority. So the term of the majority of minority is, if you also look the Mandarin textbook, they just translate as a 多数载子 or 少数载子, but sometimes also very confused because of the 载子 carrier is already kind of confusing. Then we put the 多数, 少数, and that's also another confusing. But we can just use as a example, like for example, if we look at the male student versus a female student in the NYCU, which one is the majority? For sure, the male student. We are very famous in NYCU, have a huge male student compared to female. So the majority is just a term to describe that in the certain group that which kind of which kind of things take the major part. So that's we call the majority. Which kind of things has a larger than another kind of thing. So that's we call the majority. So in the N region, what is the majority? For sure, it's electron. So in the N-type region, for sure, the electron is the majority because it's a place full of the electron. And in the P region, which one is majority? The hole is majority. By the way, it's better to use PN diode to understand the concept of the majority or minority, because usually when we talk about the majority and minority, it's in the time when you learn the BJT, bipolar junction transistor. Because bipolar junction transistor is completely dependent on the minority carrier behavior. At that moment, you will get so confused because BJT is the device, whether you have the PNP or NPN, and lots of phenomena is due to the minority. And sometimes the minority is a term you have to define by compare with the majority. So sometimes easily to get confused. So, but in the case of PN diode, it's relatively simple. So it's better you start to get a little bit sense of this concept in the PN diode. So now in the P region, for sure, the majority is a hole. So that means electron is minority in the p region. And then also in the n region, hole is minority. So now we can see the majority, the electron in this region is a majority, will start to inject in this p-n diode in the n region. But now the electron being there in the n, in the left-hand side p regions become the minority. So now you can see the majority carrier, if you completely ignore the electron holes. Some textbook they use the majority to describe everything, but it's getting confused because they will say majority in the right-hand side flow becomes a minority in the left-hand side, and then in this moment you probably will start to feel completely confused because of the definition of majority and minority sometimes have to compare with the original concentration here. So now we have the majority of electron inject into the N in the P region will become a minority, and then we have the majority holes inject into the N region will become a minority. In most of the case, we don't have to worry about the majority and minority, but the most troubling part is that there are so many secondary effects is when the minority carrier is larger than the majority. Then we got so many problems that need to be understood. But in here, we won't talk too much here. Okay, so the next one is for sure we will be interested in the reverse bias. So reverse bias is simply we just apply the negative on the anode side. That's how we call the reverse bias. And the major result is that once we apply the reverse bias, our barriers become larger, our mountains become higher, our barrier height is increased. So that means your electrons here is not possible to cross this mountain anymore, and also the holes cannot cross this mountain anymore. So based on this Venn diagram illustration, then we can expect if we have the IV curve. Now we apply the reverse. Ideally, we should have no any current. So reverse current should be very close to the zero. Of course, in reality, it's not possible, but ideally, based on this Venn diagram, that should give us expectation our reverse current should be very small and approach to the zero. So that's also can be understood by using the Venn diagram. So finally, we can complete our p-n diode characteristic as shown here. So we have a forward conduction, and we have a reverse leakage current here. But ideally, we should have the zero current, but in reality, they will still have a little bit reverse current. That's because due to certain non-ideal effects here. But this is just a typical textbook curve. But if you had a chance to fabricate or measure the diode by yourself, so our forward characteristic is roughly the same. Once we increase certain bias, we start to see the increase of current, so we define this as a forward turn-on voltage. But in the reverse, it's different. Ideally, we should have the very low reverse leakage current, but cannot always be such low, because after certain voltage, we start to see the current is shooting, and this is a moment we call as a breakdown. And the voltage we define here is called the breakdown voltage. Of course, there are lots of physics why to explain why the breakdown here. Probably we won't talk about at this moment. But also one thing is that in most of the case, you actually won't see your reverse current with such small, but usually it's gradually increase as increase your reverse bias. So this is a case because of a leakage current here. So that's pretty often to see in the device that you are doing testing or the device you are fabricating. And related to the process, although we simplify, when we talk about device physics, we only draw the p-n diode like in this way. But in reality, we cannot possible to make the diode like in this way. So usually, this is our real p-n diode looks like. So we have the p-n here. So you have this is the substrate is n. So we have a p-n here. We have a p-n here. So that's the real p-n diodes look like with considering the fabrication steps. Okay, so now we'll move to the MOSFET operation. So we have been already talking about the MOSFET in the first class. So I think at this moment should be pretty easy for everyone. So usually when we consider MOSFET, the first MOSFET is a 3-terminal device. So we have the gate, source, drain here. And then the first operation is that when we bias the gate smaller than VT, and VT here is called the threshold voltage. And because of VG is smaller, our threshold voltage, so we expect there's no current because of there's no inversion electron below the dielectric. But the one thing you have to be aware of, that's something we don't mention before, is now you see the term space charge region again. So just back to 10 minutes ago, we also talked about space charge region. And I already mentioned space charge region is in the between the P and N. And also the MOSFET, we have the many P and N junction. So that's why we also need to understand, we also need to be aware of that there's a P-N space charge region here. And the reason why it has a space charge region, because this is a P-N junction. So we have a P, we have an N, and this is P-N junction, because we have the P, we have an N here. And this P-N junction actually will play the crucial role when we try to fully understand the MOSFET. And once we apply the bias, VG is larger than threshold voltage, so we start to induce inversion electrons layer. And because right now we apply the drain bias here, so now we can expect the drain bias will start to attract the electron flow to the right. So that's a electron current. And for sure, the denote for the current is the direction of the current is the opposite direction compared to the electron current. So that's why the drain current is drawn as shown injecting inside, but actually is electron current flowing outside. So because of we have been already discussed the MOSFET, I think right now everyone can pretty easily to understand the operation of MOSFET. And for the later, we will spend some more additional time to discuss for some of the more critical part related to the IV curve in the MOSFET, because the one we have been described before is just a purely simplified case. But now if we have to take into account the space charge region in here, then that was slightly different. There was slightly additional mechanism that you guys should know. So due to the time, probably we will stop at here. So we will see each other in the next week.